Hi everybody! I guess you're watching this video because we casted the retention modeling spell on you with either one of our previous videos or one of our previous papers. Oh yeah, and while we're talking about cast, make sure to check out the cast website and the cast YouTube channel because there's a lot more information there to be found. So let me set the stage here, okay? You got intrigued by the idea of applying retention modeling and you go to the lab, you have a sample in one hand and a column in the other. You go to the lab and suddenly you think, well, what do I do now? What do I measure? As I told you in one of our previous videos, when you apply semi-empirical models, like these, you only need a small number of experiments, depending on the number of parameters of these models. The first question could then be, do I do isocratic elution or gradient elution? While many of these models have been validated with isocratic elution, gradient elution actually guarantees that your compounds will elute from the column and thus produce usable data. For that reason, I suggest that you measure 2 or 3 scanning gradients. So then of course the next question arises. What kind of gradients do I measure? The most important thing is that you have to vary the effective gradient steepness between your experiments. The effective gradient steepness can be described by this formula, which is the product of the slope of the LNK versus phi plot, described by S, the slope of the gradient, and the column volume. Ways to vary this effective gradient steepness are to change the slope of the gradient by either changing the initial or the final concentration of the modifier within the same time, or to change the total duration of the gradient. You could also change the flow rate. You could also change the column volume, but you have to make sure that you have an identical stationary phase as the column that you used before. How much different these gradients actually have to be was long thought to be a factor of 3. But in one of our recent papers, we found that the proximity of your optimized gradient to your input scans is actually much more important. In that case, if your optimized gradient is further away from your input scans, it could be a good idea to run that optimized gradient again and add that to your input scans. Oh yeah, and make sure to minimize your experimental error due to buffers or other factors, because bad data can never produce good predictions. So you did it! You did your first scanning experiments. Are you ready to perform any of the approaches we discussed in our review? Again, you can find the link to our review here, and we hope to see you in our other level 3 videos. Bye!